Welcome to the next session of the morning. I'm Javier Rodriguez from CHOM, the Third University of Madrid. I'm going to be the chairman of this session. We are going to start with the first speaker, who is Diebold from Veritas, talking about sloshing and phase transition in marine and offshore applications. So please.
Thank you very much, Mr. Chairman. So here is the title of my presentation. I will deal mainly with sloshing and at the end phase transition for sloshing. So here is a summary of my presentation. First, I would say I will give an introduction. Then we will increase the complexity progressing in this presentation. So first we'll start by global flow with some experiments and CFD calculation. Then we'll come to local flow, sloshing impact pressure. And then we will speak about a project that was initiated some years ago and where the goal of this project is to study the phase transition during sloshing impacts. And then it will be time for discussion. So first, so I hope the sound will not be too okay. Okay, so first, sloshing definition. So sloshing may be defined as the violent behavior of liquid contents in tanks submitted to the forced vessel motion on the sea. So as you see, you have a ship advancing in the waves, and inside you have some tanks which contains LNG, for instance. It is an LNG carrier, and due to the vessel motion, you have internal waves inside the tank, and what you want to avoid is the impact of the waves that could damage the containment system, and what you want absolutely to avoid is the leakage of the liquid content, because LNG is kept at a temperature of minus 160 degrees, and if there is a loss of tightness of the containment system, then the LNG, because of its very cold temperature, will make the steel of the ship brittle, and the ship will break and will lose the ship and the crew. So this is the reason why we have to study in engineering, classical engineering studies. First, we start with seakeeping analysis, where we compute the ship motions. For this kind of ships, we have to take into account the coupling between the internal liquid motion inside the tank and the ship motions. So this can be done using classical seakeeping software, such as Hydrostar that is developed in Veritas. So it relies on the potential theory. And so using this kind of approach, we can compute the coupled motion. Once we have the transfer function, we apply the meta-ocean condition, we can derive the motion time series for each degrees of freedom for the ship, and we can apply this time series motion for either sloshing model test that you can see upper right here, and you can also apply this ship motion to CFD calculation. Here you have an example of CFD calculation using open foam calculation, and you have some probes at some point that appears during the simulation. So here, during the simulation, we have a screening of the tank's boundaries, and each time the pressure exceeds the given threshold, then we store the impact in order to get, at the end of the simulation, an impact cartography. So in this presentation, I will deal mainly with sloshing experiments, but I will say some few words on how we can use these sloshing experiments in order to validate the CFD calculations. What I can say also is that in the daily practice in the industry, sloshing model test and CFD calculation are complementary, because you can see that in sloshing model test, you can put some pressure probes at some specific location, but you cannot cover all the tanks with the pressure probes, whereas with this kind of post-processing of the CFD calculation, by screening the tank's boundaries, you know all the events that occurred during the ship motions and during the simulation. So at the end, you are sure not to miss any sloshing events. So here is, I would say, the industry practice. And now we'll come to the different experiments that we have carried out in order to validate our CFD tool and in order to better understand sloshing phenomenon. So first I will start with the global flow. So as you see in Bureau Veritas and in the bibliographies that you can find on the subject, there are different kinds of tanks and configurations that were studied. So we start with a 2D harmonic test on a simple 2D tank. Then there was, I'm sorry, I have to put the cursor here, okay. So there was also some experimental benchmark consisting in carrying out very simple experiments, but that can be shared, and these experiments are published. So if anyone wants to validate CFD calculation or to perform sloshing model test, they can refer to this publication where different research institutes, universities, and companies such as Bureau Veritas or GTT participated in. Then in Bureau Veritas, in cooperation with École Centrale de Nantes, that is a French university, we carried out some tests with a 3D tank, and we perform a 3D harmonic test, and then we'll come to what we call 3D irregular test. By 3D irregular test, we mean the ship motions. We simulate the ship motions that the ship can see on the sea using a full scaling. So I will detail a little bit. So you can see for 3D harmonic test, you can see the setup. So here you have what we call Hexapod. It's a 6-leg platform which can reproduce any arbitrary motion. So for this campaign, we use the Hexapod of École Centrale de Nantes. Here the model, the scale of the model is 1 to 70. We use water and air. And for the test, we considered different filling levels. In fact, all the filling levels that the ships could encounter. So from low filling levels, what we call the 7% of the height, to till high filling levels, different amplitude, different periods of the motions, in order to test and to evaluate the nonlinearity of the phenomenon. And using this kind of measuring device, this measuring device was, which is called a global forces weighing device. It allows us to measure the global forces, meaning the integration of the pressure over the tank's boundaries. So it's a global force that we have measured, and here on the graph you can see a comparison between CFD calculation relying on open foam and the experiments, and you can see that the agreement for at least one motion was very good. So in a publication, we show all the cases that we have tested. So it was more than 500 cases. Each case represents 15 periods of motions. And we validate that the CFD is capable to predict accurately the force motion, whatever the filling level, whatever the amplitude of the motion, whatever the period of the motion. Okay. So now we come to a real case, I would say, because before it was just a very simple cosine motion, and now we come to real motions that the ship could encounter during its lifetime. And so here is the case that we have considered. So it's a severe case with the wave height equal to 10 meters, so it corresponds to a storm, more or less. And you have here the ship hull geometry that is represented. So here it is, you have a comparison between the experiment and the CFD calculation. It's a 3D case using open foam. For this validation, we considered, we perform a sensitivity analysis in order to study the convergence in terms of number of cells of the CFD calculation. And here you have a comparison between, for the global forces still, between the experiments in red and the 4 CFD calculation with a different number of cells. So it's difficult to represent the whole time series because in naval architecture we are used to represent the lifetime of a ship in 2 blocks of 3 hours. So here the simulation at full scale was 3 hours. So you have to use full scaling in order to evaluate the time that we spend in the experiment, which was approximately 50 minutes for the scale 1 to 70. And here, in order to represent the distribution of these global forces, we pick up the extrema and we can plot the exceeding probability function of these global forces extrema. And you can see that when you increase the number of cells, you tend towards the experimental distribution of the global forces maxima. So at this stage, we say that using OpenFOAM, we have a good accuracy for the global flow within the tank, and for us, CFD is validated for the global flow. So now I will come to local flow. So for local flow, I will mention the NICE experiment that was initiated some years ago in 2012 by the French company that designed the containment system for LNG carriers, namely GTT. And so we start with a very simple geometry. So it is a geometry that you can find in the paper. So it's approximately 1 meter in breadth. It's a slice of LNG tank. The scale would be 1 to 40 in comparison with a real LNG tank. We'll use water and air, and one filling level was tested. Different kinds of motion were tested. Simple impact wave. By simple impact wave, we mean very simple displacement that lasts 2 seconds. It's a back-end force motion in order to create an impact on the ceiling of the tank. And we put some pressure probes at the ceiling of the tank, and then we can compare between participants the pressures. It was the main objective of this experimental benchmark, but we also carried out harmonic test and irregular test. So different parameters were tightly controlled during this experiment. It was the tank positioning, the filling level, and also the actual motion of the platform. So this was checked during this experiment. And as a measurement device, we use a high-speed camera with 1,000 frames per second, pressure sensors, and there were from 16 to 72 pressure sensors, with a sampling rate of 20 kilohertz. So you can have a look on the different, so here it is the hexapod that was used during the experiment. You have a look on the tank that was tested. The pressure sensors, for our needs, we used, in BV, we had only 16 pressure sensors, so we use our 16 pressure sensors with a sampling rate of 20 kilohertz. That is a minimum in order to capture the dynamics of the impact. We use also the global forces balance in order to measure the global forces. As I said, we have a video camera with 1,000 frames per second, and there was also the use of a motion control in order to check the motion of the tank during the experiments. So here you have an example of the test that is called a simple impact wave. So you can see that the motion is very short. You have the case that was reproduced in a CFD. Here it is a classical video camera, so only 25 frames per second. And what was very nice in this case is that we, during the impact, we isolated air pocket impact. And so the pressure sensors were located in the air pocket. So meaning that all the pressure sensors were measuring the same pressure because they are in the air pocket. So this experiment was very nice in order to validate and calibrate the pressure sensors, I would say. It's also a very good model because for this kind of experiments, here you can see, here you can see a comparison between the different participants. So for the first peak maxima, you can see that there is agreement. It's not perfect, but in comparison with the other tests, we can say that it's nearly perfect. So you can see that for this impact, for all our 16 pressure sensors gives the same pressure trace because they are in the air pocket. So it's a very good model because the time duration of this motion is very short, and so we can compare very easily CFD calculation. If there is a compressible model, we have to introduce a compressible model because the air pocket is compressed during the impact. And if you want to check your compressible model for your CFD calculation, this is a very nice case. So it's what we did, and the agreement was, I would say, reasonable. There were, so the case that I have just shown you, it was, I would say, simple, a case for which we had a very good agreement. Now we come to a case, if I repeat this, so here we have the video camera with a high-speed video camera, and here you have a zoom on the impact. So here, here it is the ceiling of the tank, and you can see that we have an inclined free surface with a kind of a Wagner impact because you have an inclined free surface with respect to the ceiling. So we thought that it would be quite easy to compare with maybe a Wagner model, but also we thought that it was quite easy as a test case to compare between the different participants. But if we now compare the pressure measurements, you can see that between the participants, so I will not detail too much the participants, but there were some French university, Nantes, with the university with Bureau Veritas. So there was the University of Marseille, the French company GTT will design the cargo containment system, Norwegian University SINTEF, and Korean and Spanish and Chinese universities participated in this experimental benchmark. And you can see that there is quite large discrepancies among the different participants for a very simple motion and so for a very simple impact. So now if we zoom a little bit, so sorry, here we have the ceiling corner, and you can see, because there were of course some repetition of this test in order to see what was the repeatability of the test. That is very important. And you can see that depending of the participants, so there were 10 repetitions of the test, and we can see that there were large discrepancies for exactly the same motion, a priori. So these results were quite disappointed. It was during the first year. So during the second year, there was a repetition. And from this test, we can see that the best, at least the tests that are the most repetitive, come from the French company which designed the cargo containment system, namely GTT, who is, this company is quite experienced in sloshing model tests because it is their daily practice. They have 4 hexapods running 24 hours per day. So we could give some confidence, but in order to check and to compare, we decided to carry out a CFD calculation using OpenFOAM, and indeed, taking into account the size of the pressure sensor, when we compare the CFD calculation in red with the experiments in blue, we had quite good agreements, except close to the corner. Close to the corner, the agreement was not so good. Still, it needs to be explained, but afterwards, we had a quite good agreement between our CFD calculation and the model test carried out by GTT, which were the most repeatable. So it gives us some confidence in this model test and also CFD calculations. So at this stage, we can say that the conclusion of this experimental benchmark is that carrying out sloshing model test is not an easy task. There are many constraints about the data acquisition system because we need to ensure that, for instance, the sampling rate of the pressure sensors is high enough to capture the dynamics of the impact. Also, there was a strong focus on the signal processing of the pressure sensors. Many mistakes can be done when we post-process these results. Also, the filling level need to be carefully looked at, the tank alignment. So all this was checked, but we need to be very careful. So this ISOP sloshing benchmark enables comparison between different companies, research institute, and this sloshing benchmark is a very good basis for CFD validation, because with this simple impact wave, as you saw, we have a very short duration of motion, and we can calibrate CFD for using compressible model or other kind of impact. And the final conclusion is that CFD users should be aware about the sloshing test complexity before any comparison with CFD. So, of course, they may have some discrepancies between the numerical calculation and the experiments, but the experiment should report the repeatability of the test, and this is not often reported in the literature. So now we'll increase a little bit the complexity of the sloshing model test, and we'll say we'll speak about the phase transition during sloshing impact, and we'll talk about the sling and Diebold projects. So during sloshing impact, the main governing parameters are in terms of dimensionless numbers, the fruit scaling, the density ratio, so the density of the gas divided by the density of the liquid, the gas Mach number, the Weber number, the Reynolds number, and the Jacob number. During the project Sling Diebold that I will talk about, we put the focus on the density ratio between the gas and the liquid, the gas compressibility, and the phase change during the sloshing impact. So all these questions refer to the extrapolation of the model test to the full scale. As I said, usually we carried out a sloshing model test for a tank that is 1 meter in breadth. So the scale here in comparison with the full scale is 1 to 40. So once we have measured the pressure sensors, how to extrapolate from model to full scale. So we need to take into account, and in the next slides, we will talk about the gas compressibility, the density ratio, and the phase transition. So in actual sloshing model test, the gas compressibility is too high at model scale. The density ratio, so the density of the gas divided by the density of the liquid in the model test and in reality is the same. And the phase transition is not present at a model scale. So we'll see what could be the influence of this phase transition during sloshing impact. So for this, some years ago, in 2015-16, there was a project initiated by Marine, a research maritime Dutch institute. And these companies, so GTT, who is a French company which designed the containment system for LNG carriers, but there was also Shell, Total, classification societies such as Bureau Veritas, the Chinese classification society, and so on. And so we wanted to study more in detail these governing parameters, the density ratio, the gas compressibility, and the phase transition. With the aim also, because now we know that we have a good return of experience on LNG carriers, so on all ships transporting LNG, but now because of decarbonation, we have a new fuels that comes into the game, such as liquefied hydrogen, liquefied carbon dioxide, ammonia, or methanol. And so all these companies are interested in these new fuels, so we want to better understand the physics. So we decided to design this kind of experimental device that is, sorry, I will put again the video. So that is quite impressive. So it consists into, you have an autoclave which is approximately 20 meters long, in which we have put a flume tank. And within this autoclave, it consists in a controlled environment where you can play on the pressure and the temperature in order to be able to be on the phase transition curve for the water, and in order to be able to have a condensation or evaporation during sloshing impact, in order to study phase transition during sloshing impact. So this project was a little bit delayed during the COVID, but now we have the results, and some additional results are ongoing. So these projects are called Sling-Imbol. Devaraj van der Meer, professor from University of Twente, is responsible for the Imbol project, and it is a continuation of this Sling project. So you can see that is quite impressive. The diameter of this autoclave is 2.5 meters. So inside this autoclave, as I said, the temperature can vary from 15 to 200 degrees. The hull edge pressure inside the autoclave can vary from very low pressure to high pressure, 10 bars, namely. And the gas composition can vary inside this autoclave. One can put nitrogen, argon, SF6, and also we have, and the liquid of interest is water. So inside this autoclave, we have a flume tank with a wave maker, which is a piston type wave maker. And you have a beach in order to facilitate the wave breaking. And here you have at the end a wall equipped with pressure sensors, with a high-speed camera, in order to film and to record the impact. So how do we, in practice, we can, during this experiment, because we can play on the pressure and temperature, we can go along this saturation curve. That is quite important in order to study phase transition during the impact, because I have to remind you that for LNG and liquefied hydrogen, it is cryogenic fluids that are in equilibrium with the vapor. And if we also want to study the density ratio, we can increase the hull edge pressure, and for this we start from the phase transition curve, and slightly we can put a non-condensable gas on top of the water vapor, and namely for the experiment that I will show you, nitrogen was considered. And by doing so, we can increase the hull edge pressure, and the hull edge pressure is related with the density ratio between the gas and the liquid, and as you will see, density ratio is a governing parameter for sloshing. So now I will show you for, so we used as a motion for the wave maker, we use the motion that comes from seakeeping analysis of a ship. So even if we cannot consider this experiment because in a real tank you have the two boundaries that move together, but here of course there is only the wave maker that moves, but anyhow we try to simulate what could be the motion inside the LNG tank by considering actual motion using fruit scaling. So it's what we did. So we have a long I would say wave maker motion during 3 hours at full scale. So it was a wave maker signal that was considered. And here we consider at the ambient temperature, after we'll see, and it's ongoing, we'll study all the cases in the rest of this space. But here, in this presentation, I show only result at the ambient temperature. So we increase, so the parameter that is changing, it is the density ratio. We start from a very low density ratio and we increase the Hurley pressure, and so we increase the density ratio. And we will see the result. So here we measure the pressure. Using a pressure probes, and we can plot the exceeding probability function for the different cases that we have tested. And you can see, in the X scale, we have the pressure. So we can see that it's going to close to 100 bars. And on the Y-axis, you have the probability. And so it's called exceeding probability function. And you can see that when you increase the density ratio, then the pressure are reduced a lot. So for very low density ratio, you may record some pressures up to 80 or 90 bars. And for the same liquid, for the same wave maker motion, and if you increase just the density ratio, so meaning the density of the gas divided by the density of the liquid, so if the gas is heavier, then you can mitigate a lot the sloshing pressure. And so here, in blue, you have the curves that you would get with the density ratio of air and water, and in black, it is the curves that you have with the density ratio of the LNG. So you can see that if you want to properly take into account, and if you want to study LNG, you need to take into account this density ratio in your sloshing experiment. Otherwise, if you consider air and water, you may measure too large pressures. So here it is another way, to represent this fact. So on the x-axis, you have the density ratio, and when you increase the density ratio, then the pressure the sloshing impact pressures decrease a lot. And so the interest of the industry is to study the liquefied hydrogen, for which the density ratio is even larger, so we can expect that there will be a further decrease of the sloshing pressures. So in order to explain this decreasing of the pressure according to the increasing of the density ratio, we came back to very simple impacting wave shapes. And this is the reason why here we studied solitons. So we can generate solitons with the same wave maker signal, and we can study what is the global wave shape for these solitons according to the density ratio. So namely, for some density ratios, the global wave shape just before the impact is strictly identical, but we also noticed that there was a decreasing of the pressure when we increase the density ratio. But today I will put the focus on this experiment where we are very close to the saturation curve, and we saw that on the curve, on the irregular test, this point close to the saturation curve give very large impact pressures. And we also verify with these very simple cases with this soliton that the pressure associated with this soliton can be quite large. And indeed, here you have a plot with the time on the x-axis, and on the y-axis you have the height of the pressure sensor. So there was some pressure sensor from the bottom to the top. And you can see that we can record very large pressures, even with this very simple soliton of 42 bars. So what can be also observed is that, on the contrary to the other cases, we have a kind of gas pocket here, but during the impact, the pocket fully collapses, what is not the case with the other density ratio. We have a pressure raise, and the shock wave can be seen, and we have a very large pressure at the bottom of the wall. So now I will come back to the other cases. Yeah, it's finished. It's finished. Sorry. And so you can see that here for the other cases where you have a larger density ratios, where you are far away from the saturation curve, you can see that you have a gas pocket that is compressed, dilated, compressed, but it doesn't collapse. whereas when you are close to the saturation curve, you have full collapse of the vapor pocket, which leads to a very large pressure. So we will continue the test by considering all the test matrix. So here today we presented only few cases, so it will be for another presentation. And now it is time for discussion. So I told you about the different complexities that we can have with sloshing model test. It starts from global flow that is well suited to validate the CFD calculation, to local flow, where we can see that when we speak in terms of sloshing pressure, we may have some difficulties to have repeatable tests. And we end with this sling ball, where the final objective is to study the influence of phase transition during sloshing impact. For the industry, we can see that for liquefied hydrogen, as the density ratio is quite high, it's a good sign that the sloshing pressures will be mitigated, but still we need to further investigate the phase transition with a larger density ratio before any conclusion. And that was the conclusion. Thank you.